Our next speaker will be Jared Rivet, for Rankin Cycle.
How are you doing today? My name is Jared Rivet, and I'm the reporter for the Rankin Cycle experiment we did Tuesday. So just an overall objective. The main objective of this lab is to understand the different components of the Rankin cycle, and then measure the relevant data and then the efficiency observed for the experiment we did in class. This figure on the left is just kind of a schematic of the different states of the Rankin cycle. You have the pump where you compress your fluid, the steam generator, which is the boiler that was missing from the experiment on Tuesday, that adds heat into the system, the turbine, which is work out, and then the condenser, which is where you cool off the steam. Over here is the PV diagram and the TS diagram. These were helpful when computing the enthalpies for the different states. So the equipment, this is the Rankin cycler experiment, which was in the lab, is actually down, and the guy that assisted said the company's actually being audited by ASME. They've had a bunch of boiler leaks, like not just us. So I thought that was pretty interesting, that that's not just the isolated thing with us. So you can see your condenser tower. This thing right here which was missing was the boiler. That was being sent out for repair. One of the tubes was leaking, I believe. And then the table allows you to put a load on it and lets you capture data for the generator. So a bunch of different raw data was collected. I think it was fuel, pressures, temperatures, speed of the turbine, and then the current and voltage readings from the table when you set the load on it. So this is just a couple graphs that are going to go through and show the data that was taken from that. So this is fuel flow from the propane gas tank to the boiler. This is the boiler temperature over time. It's a pretty linear increase in temperature as you go through. I'll talk about where steady state was at the end. It's kind of hard to see on these first like 5 or 6 graphs, but at the end it's pretty easy. Boiler pressure versus time. So you see we initially ramped it up, and then once you started letting the steam cycle through the system, it went down. Turbine pressure versus time. So that top one is your inlet pressure, and the bottom line is your exit. Temperature versus time, again, top one's inlet, bottom one's exit. This is the DC current output versus time. So this is a little bit easier to see where steady state was. It was about from a little bit over 22,600 seconds to like 22,200 seconds. Again, voltage you can see pretty easily. It's in that same range as well. And then finally, the turbine speed was what I was able to really see where we're at steady state from. It's in that same time frame. So the data analysis point from where I was, or from that last graph, I basically just took the end and the beginning and then just divided by 2 and did the analysis point in the middle. These are the data from that point in the middle. I'm not going to go through all of them, but these were basically used to go through the steam tables and then figure out the different enthalpies, entropies, specific volumes to determine like the work in, work out, heat in, heat out. So talking about that, the first thing I had to do was analyze what the boiler heat flow was. So you just found the enthalpy after the steam left the boiler and then before it came in. This was just used from the steam tables. And found that QM was 2,502 kilojoules per kilogram. Next thing I analyzed was the turbine work and then the generator efficiency. So for the turbine work, again, just using, you had to use entropy that time, and then enthalpy, which came from the steam tables. We actually had 2-phase. It wasn't totally steam. It was some water. It was in the bell curve. Far right, superheated steam. We were on like the saturated vapor line, so it was actually I think 94% steam and like 4% water, or 6% water, something like that. So the workout from the turbine was 378 kilojoules per kilogram, and then the generator efficiency. So I found the power generated in the generator was 2.31 watts. Couldn't figure out what the power or the work rate was for the turbine from the data I had, since we didn't really do the experiment. We just kind of had the data. I kind of did the best I had, so I'll just disclose that. So again, this was, like I said, used enthalpies, entropies, specific volume for one portion of it, for the different states. So as you can see, I mean, the pressures were just the ones that recorded 2 psig leaving the turbine. The boiler pressure, which is 135, 110, and the temperatures. And it was really easy to just kind of go along in the steam tables and figure out what the enthalpies were from that to figure out the heat input in the boiler and the work out. Thermal efficiency of the system, so this is another case where you use the enthalpies. Basically just figure out the work done by the cycle divided by the heat you had to put into it. And the efficiency I calculated for the data I had was 15%, so pretty low. Not great, but nothing's going to be 100% real life. So there was some uncertainty for doing this, at least for me. I mean, not having done the experiment, just kind of looking at the data, there was some uncertainty there. I had to look a few things up. Reed and Evan were both great about getting back to me last night for some questions I had. So there was definitely probably some calculation error, even just instrumentation error from all the different, I think it was like 7 or 8 different streams of data that was being collected. And then some of the assumed quantities, maybe that I used in steam tables, I didn't interpolate anything. So there could be some error there, I just kind of averaged it. And like I said, at the point after the steam left the turbine, I don't know that I was perfectly right on with calculating, like it was 94% steam and 4% condensate, or 96% condensate. It was pretty close to the border, so there may be some error there. And then in conclusion, so the Rankine cycle is used for a majority of the power generation in the U.S., so it's definitely a good experience to kind of run that cycle firsthand, or see the data and what happens as you go through the 4 different states for real-world application. So, any questions?
What do you think, where do you use an efficiency? Because you're showing 15%.
Probably out of the turbine.
How was it?
Yeah. Going for that, and then probably going from the turbine to the generator as well. That was where I was
think
assuming.
that, the cycle efficiency is around 30%.
Really?
Yeah. So, you're showing
Maybe it was that
15%.
boiler leak, I don't know.
Yeah. Then
Well,
you
that-
have the data from the previous class, right?
Right, well, from whenever they did it like a couple weeks ago, but I don't know if the tube was leaking at that point or not. So I don't know how that would affect it, I don't know. Can't really speculate, 'cause I didn't actually run it, I mean, we were there for a couple of minutes, so. But if I had to guess, I mean, it would be at the turbine and then again to the generator. So, any questions? All right, cool, thank you all.